Okay, good day student. I would like to continue my lecture with the volume concept of 3D seismic data. So let's have a look on the slides that I've prepared. This lecture will cover our course learning outcome 3 to get familiar with the seismic interpretation software. And in this lecture, what we will do is we will learn about the concept and know what is the difference between 3D and seismic 2D. And also will include the voxel, pixels, and colors. So in 3D is a method of seismic interpretation which involve a three-dimensional space by applying various levels of transparency of the data. So as you can see, in this data set we have inline, cross line, and also in a time view. So the third dimension of this seismic data is the time view, where you can see the changes of the data from top view, from a plane view. The volume concept involves where the interpreter will be working directly with a volume rather than interpolating a volumetric interpretation from a widely spaced grid observation. So this is where you have a whole concept of the inline, cross line, and your time. In this subsurface seismic wave field, the wiggles are closely sampled in every direction so that there will be no loops that can provide gaps in between your data. So this is where you don't have to interpolate your data, you don't have to just imagine what happened in between. This is where in 3D data you can see exactly what is happening inside the subsurface. This avoid ambiguity, and we can reduce our guessing, and it's definitely give us more details and more correct interpretation. However, because it involves 3 dimensions, we have more data, more space to be included. This is where you have to have a number. The number of volume that you have to interpret will include number of lines, which is your inlines, times the number of cross lines, times the number of time samples. As you see, we have sometimes 2 millisecond time samples or 4 millisecond time samples, and also the number of data types. If we have different data types, it will be more. So in this 3D volume concept, we can apply innovative approach, not just by interpreting the horizons and structures. We can also use selected slices. We can also use automatic tracking. This will help us to comprehend our information that we have in the data, so that we use all of them to provide a better model comparing to the 2D. By saying this, it doesn't mean that 2D is not good. 2D is sometimes better than 3D because the overwhelming of the data sometimes get people confused. In the yesteryears, we are still using 2D, and 2D still provide better interpretation sometimes. So we should not be neglecting the 2D parts of seismic because we have now 3D. But we should use 3D to improve our interpretation. So as I mentioned, in 3D data volume, what we have is we have a cross line, the line or inline, and also a cross section. Also a time slice, a time view, map view. The 3 steps of these are orthogonal slices through the data. As you can see, the cross lines looks mainly flat, while in the inline we can detect some displacement or some structural. This is because usually the line or the inline is usually parallel to the strike direction or to the acquisition line, which is the sail lines, where you have your boats, there you tow your receivers. This is where the directions of your inlines, and it is usually parallel to the sail lines. In the other way, cross line is just the imaginary lines that we use mathematical calculations to combine the receivers the data that we receive from all receivers, and then we stack it and become a cross-line information. So in a 3D data set, seismic data set, the basic information that we should have is the inline, which is the vertical section in the direction of the boat movement or cable layout, and the cross-line, which is the vertical section perpendicular to this direction, and a time slice, which is known as a depth or slice section. Apart from that, because we have a 3D data and we are working with software, so we can make use of this 3D data by having diagonal line, arbitrary lines, horizon slices, box slices, and more attributes that we are going to learn in this subject. So this diagonal line and arbitrary lines is very important, because if you have few wells in your 3D data set, then you can use this diagonal line and arbitrary lines to connect between your between your three different well locations, and then you can produce an imaginary line to see what is the subsurface connecting between these three wells. For 3D data volume, we can have several display products, so you can see more, such as I mentioned, arbitrary line, cross-line, depth slice, horizon slice, seismic attribute display, and also you can also combine multi-attributes in one display that we call it as a composite display. Each seismic data set is stored in voxels. This is known as volume pixels elements. Voxels is just like a cube representing a seismic samples. The dimension of this cube, if you can imagine this cube is one data set, it is the dimension will be represented by the inline, cross line, and also the time or depth sample spacing. All seismic data open in Petrel or in any interpretation software can be converted to an 8-bit voxel volume. The original attribute values of each samples will be assigned to new voxel value. This means that how much data will be converted to an 8-bit voxel value. As an example, once you have your seismic data, 3D, you load it into the interpretation software, it will be converted to an 8-bit voxel volume. How? By dividing the original attribute data by 256 and assigning the group data to a single voxel, to a single value. The data is not clipped, means that the data is still there, it's not being removed, it's just being assigned to a single cube. As an example here, for a 16-bit volume with the data range of negative 32,000 to positive 32,000, the total of this data is 64,000 because we include the range from negative and positive. So the original attribute numbers in this seismic data was 64,000. So once it is loaded into any interpretation software, the numbers will be reduced to 256 because we were in the we reduce it into 256 cubes or pixels. Each pixels will be assigned with 251 samples. So you have 256 cubes and each cube have 251 samples. In the 16-bit examples, the lowest original attribute value will be the negative 32,000 and the highest will be the positive 32,000. So the lowest value will be assigned to the first voxels, which is voxel number 1, followed by the following. So in examples, the attribute values of negative 32,000 to 31,000 will be assigned to the same voxel value of 31,000. So means the range from 31,931 minus negative 32,182 is just like when you use your calculator. Let's try and do something, little mathematics here. So you have negative 32, so I just ignore the word negative, minus 31,931. You have the first 251 samples value this will be assigned to cube number 1, followed by the rest until the last cube, which is cube number 256. The cube that I'm saying here is especially referring to your voxels. So we have 256 voxels, and these voxels has different colors and opacity that will be applied to all the samples assigned in each of these voxels. It's just like your pixels when we have your image. Okay, as examples here, you have your traces. So these traces, in the first voxels, it has this value of the first 251 samples, followed by the next 251 samples. So this diagram can explain better, as it shows that from time 0 to 3000 millisecond, the first few samples, the first 251 samples is assigned to the first voxels. Followed by the next 251 samples is assigned to the second voxels. This is continuous up to the end of the data, where the total numbers of the columns for the voxels will be 256. So you can see here, this is your seismic trace, where you have your positive loop and your negative loop. Your seismic trace in green color, and you can see the changes is some at the peak is high amplitude, and this is also high amplitude in negative value, and these cubes are represented by inline, cross line, and depth section. So each samples is at the center of the voxels, and the sample number is from 1 to 251 goes to the first cube. The rest will go to the second cube, followed by the rest next 251 will go to the third cube until the end of your data. So this is how you store your seismic data. Just imagine how many traces are in your one seismic data. If we have a 3D, you have to calculate your inline direction and also cross-line direction. So voxel values application is usually very important for unconventional seismic attributes, where we can use geobody interpretation, we can use this for fracture characterization, carbonate characterization, and so on. So these voxels, as I mentioned just now, is also represented by different colors. So the colors have, let's say, yellow will be assigned to the first cube, light, and so on. So if we have this voxel values application, we can see that we have a geobody where we have a Petrel seismic sampling. This is a horizon that we can categorize. This is where we can see the phases changes in between, let's say, sandstone and shaly sandstone. So this helps to improve our interpretation. Apart from that, we also use voxels values not just in seismic data. We can also we actually apply this voxels values application in non-seismic data, such as the gravity data, resistivity data, where we apply some colors, and you can see there are pixels in between these colors that represented by different shadings. So voxels values application is, you can see here, in a bit depth, unassigned 8-bit, signed 16-bit, and signed 32-bit, the maximum range of data that can fit in the one of the voxels is from this value only. So if you have a better computer system, that nowadays we have a 64 bits, so you're going to have more dynamic range of data that can be stored. So usually we are more than this because we have a better computer system. So in a dynamic range of interpretation, large numbers, this is represented by a seismic trace. So this is known as amplitude curve. So this amplitude curve, I will teach you guys during the seismic amplitude attributes in the next few slides, in the other slides.